Hello everybody, my name is Calvin with student ID number of 22055311140. I am currently studying mechanical engineering in Udayana University. And in this video, I am going to present about polymers for the assignment of engineering materials knowledge subject lectured by Professor Dr. Tjokorda di Tirta Nindhia, STMT. All the materials that were used in this presentation were taken from this book entitled Science of Engineering Materials, Volume 2 by Manas Chanda. The content that will be discussed in this presentation is thermal transitions of polymers, designing polymers structure for improved properties, and composite materials incorporating polymers. First one is thermal transitions of polymers. Evidently, for a highly crystalline polymer, only crystalline melting would be observed, and for a completely amorphous polymer, only glass transition would be observed. Most polymers are, however, semi-crystalline and fall in between these two extremes. They are therefore characterized by both types of transition temperatures, with Tm being the melting temperature of the crystalline domains of a polymer sample, and Tg is being the temperature at which amorphous domains of the sample undergo glass transition. The transition in specific volume with temperature for a semi-crystalline polymer is represented by the curve ABGHI in this figure. This is a determination of glass transition and crystalline melting temperatures by changes in specific volume scheme, with A is a liquid region, B is a liquid in some elastic responses, BE is rubbery region, and EF is glass region. GH is crystallized in rubbery matrix, and HI is crystallized in a glassy matrix, and CD is full crystalline solid. When the melt of polymer is cold, rotational and vibrational energies of the polymer molecules decrease and the total energies of the molecules have fallen to the point where the translational and rotational energies are essentially zero, which is now crystallization is possible. Crystallization, however, occurs if certain symmetry requirements are met and the molecules are able to pack into an ordered arrangement, in this case of semi-crystalline polymers. Crystallization occurs only over portions of polymer chains resulting in crystalline regions, or so-called crystallites, separated by amorphous regions. The energies of the molecules continue to decrease as the temperature decreases further below Tm, until the temperature Tg is finally reached, at which the wriggling motions of the polymer chain segments in the amorphous regions stop due to cessation of bond rotations. Below Tg, the amorphous regions are therefore no longer flexible and become hard and brittle, like a glass solid. Next is designing polymer structure for improved properties. The three principles that are applied to give strength and resistance to polymers are crystallization, cross-linking, and increasing intense stiffness of polymer molecules. Combination of any two or all of the three strengthening principles have role in achieving various properties with polymers as seen in this figure. The three basic principles: crystallization, cross-linking, and chain stiffening for making polymers strong and temperature resistant are represented at the three corners of the triangle. The sides and the center of the triangle indicate various combinations of the principles. For polymers composed inherently flexible chains, crystallization and cross-linking are the only available means to enhance polymer properties. A third and relatively new strengthening principle is to increase chain stiffness. One possible way of stiffening a polymer chain is to hang bulky side group on the chain to restrict bending. However, the disadvantage of attaching bulky side groups is that the material dissolves in solvents very easily and undergo swelling. Since the bulky side groups allow ready penetration by solvents and swelling agents, this problem can be eliminated by stiffening the backbone of the chain itself. One method to do this is to introduce rigid ring structures in the polymer chain. The combination of all the three principles mentioned above is led to the development of new and interesting products with enhanced properties. Next is composite materials incorporating polymers. By combining two or more materials with complementary properties, a composite material can often be produced which is better than or even radically different from components alone in terms of strength or resistance to heat or some other desirable quality. The principle of composite materials has led to the design of and manufacture of a new range of supermaterials with far-reaching effects on engineering and construction. The principal attraction of composite materials is their superior combination of lightness, stiffness, strength, and ductility. The component of such a material may belong to diverse classes of materials like metals, ceramics, glasses, and polymers. The best combinations of strength and ductility can be achieved in composite, which consists of a fibrous component embedded in the ductile material. The embedded component may also be in the form of particles and sheets. Under stress, the metric material tends to flow out, but in doing so, it produces a frictional force on the embedded component, which contributes to the strength of the composite material. Some examples of the composite materials involving polymer are given below. Bakelite is a phenolic resin filled with fillers which are used to improve its properties and also to reduce the cost. GRP or glass reinforced plastics are composites which use glass fiber in the form of rovings, chopped strand and mat to provide the great strength in the resin to transfer stress to the fiber and reduce brittleness. Wood itself is a natural composite, consisting of fibers of a highly crystalline cellulose polymer in a matrix of lignin, which is non-carbohydrate natural binder for the cellulose fibers. Plywood is a composite consisting of thin wood veneer bonded with a synthetic resin. Vehicle tires are composites containing woven cord reinforcement to strengthen the rubber. Cellular polymers, also called polymer foams, have honeycomb structures containing large number of air cells, with the result that they have extraordinary lightness combined with strength, depending on the amount of polymer per unit volume. Thank you for listening to my presentation. If there is something wrong that I said in this presentation, feel free to correct me in the comment section. Thank you.